A concept
of doubts.
Yes. Questions.
Sir, in the minor, we have not got response of the queries.
Well, regarding the queries, I'll answer them on Saturdays and Sundays. I'm very sorry. I'll do that. All the queries, all these things will be answered in Saturdays and Sundays. Any other questions? Okay, fine. So in the last class, we introduced what is known as almost everywhere. Right. So you have measure space. So we defined what is known as mu almost everywhere, or sometimes we write it as mu a dot e, or simply a dot e, if the measure is understood. Correct. Well, let's look at a simple example. 1, if x is, f from, let's say, R to C. Fx is 1 if x is rational, 0 if x belongs to Q complement. Right. What is the bound for f?
1.
1. Right. So f is bounded by 1. Right. Right. So what is the essential bound? That means it is bounded almost everywhere by maybe I'll put it as something else so that things will be easy. Half. So f is bounded by 1, but f is almost everywhere bounded by
Half.
half. Exactly. It is not bounded by half, but it is almost everywhere bounded by half. Is this clear for everyone? Atharva?
Yes, sir.
Others? Is it clear? Because this is one of the important concepts.
Yes, sir.
This notion of almost everywhere is one of the important concepts which we are going to use again and again and again. See, in the context of what is known as Riemann integration, we saw this. What is that? Well, f is a positive function. Positive function. What can you say about f? F is greater than or equal to 0 and integral a to b fx dx is 0. What can you say about the function?
Zero.
No, if f is continuous. And if f is continuous, then f is 0, identically 0. If f is not continuous, we saw an example of a function which is not continuous, but still the integral is 0.
Sir, it is discontinuous at countable many points.
Huh?
F may be discontinuous at countable many points. I mean.
Right, that's right. So, but in another few classes, we are going to see that integral a to b fx d mu x or integral over and set omega fx d mu x is 0 implies, and if f is positive, then that should imply that f is not 0, but it is 0 almost everywhere. This is one of the important concepts which is going to play an important role in many places. Right. Fine. So in the last class, we introduced a concept. What is that concept that we introduced? We introduced what is known as almost everywhere convergence. Right. So Fn converges to F almost everywhere if measure of the set, all those x and omega, such that Fnx doesn't converge to Fx has got measure 0. Right. And we saw examples. Right. And then we defined what is known as set of convergence. So this is the set of convergence. So under the assumption that all these Fn's are measurable, we saw that E is measurable. That means this E is a part of the sigma algebra. All these we saw. Right. In fact, we wrote this E in a different fashion. Fine. Now let's proceed further. So let's begin with a lemma. We know this one, that if Fn converges to F pointwise, then F is measurable. The limit is measurable. The limiting function, that is F, is measurable. Now, if Fn converges to F almost everywhere, what can we say about F? So let Fn be a sequence of R bar valued Borel measurable functions defined on a complete measure space. Omega A if Fn converges to F almost everywhere, then F is measurable. Proof. Right. So let E equal to all those x and omega such that Fn x converges to Fx. Right. Now, the fundamental assumption is that this is a sequence of R bar valued Borel measurable functions, and therefore, so this is our assumption. Therefore, by assumption, that these functions are Borel measurable implies that the set E is measurable. That is, E belongs to E. Right. Also, as Fn converges to F almost everywhere, it follows that mu of E complement is 0. These two things. Right. So we have these two things. Fine. Now our aim is to show that F is measurable. Right. That is Borel measurable. So let A subset of BR bar, sorry, A belong to BR bar. Then F inverse of A. What is F inverse of A? All those x in omega such that Fx belongs to A. So this one can write it as all those x in E such that Fx belongs to A union with all those x in E complement such that Fx belongs to A. Right. Now on E, what do we know about E? Fn converges to F pointwise, and therefore F restricted to E is AE measurable. What is AE? What is AE?
E intersecting with every element of sigma algebra.
Right, exactly. Therefore, all those x in E such that Fx belongs to A is an element, is a set from E. Now, since E belongs to A, this implies that AE is contained in A, which implies that this set, all those x in E, such that Fx belongs to A, belongs to script A. Right. Now, on the other hand, set of all x in omega, sorry, a set of all x in E complement says that Fx belongs to A. This is part of E complement, and measure of E complement is 0. And since omega A mu is complete, so what does that tell us? Huh?
Every subset of E complement will be in the sigma
Every
algebra.
set of E complement is part of the sigma algebra. In particular, this set. It follows that all those x in E complement such that Fx belongs to A belongs to script A. Thus, F inverse of A, which is equal to all those x in E such that Fx belongs to A union with x in E complement such that Fx belongs to A, this belongs to A. That's it. That means Fs, well, since A subset of A in B R bar is arbitrary, it follows that F is Borel measurable. When you write an answer, make sure that you explain each and every word that you are writing. Please make sure that you explain each and every word. Do not say that obvious, clear, it can be easily done. Who will do that? Is it my job or your job? It can be easily done. Do not use these words in the exam. For many of you, mod f is 1 and therefore it is Riemann integrable. Why is it Riemann integrable? Constant function. It's a continuous function. Can't you not write one line? These are the things that are expected. It clearly follows. From where? How? It can be easily seen. Who should see that? I am writing it here because I want each one of you to do it on your own. Therefore, I am writing it. Right. So let me proceed. So if you look at this lemma and even the proof, we have made use of this fact that the space is this space, measure space is a complete measure space, that we have made use of it. So can we avoid this completeness? So let's look at an example. So let A mu be a measure space which is not complete. Right. So what do you mean by it is not complete?
There exists an E belonging to sigma algebra A whose measure is 0, but there is a subset of E which is not in the sigma algebra.
Exactly. So since the triplet or this measure space is not complete, there exists E in A with mu of E equal to 0 and B subset of E such that B doesn't belong to E. So we are going to make use of this fact. Right. So now define f from omega to R as fx equal to 3. Well, it doesn't matter. You choose any three different numbers. If x belongs to B, 2 if x belongs to E minus B, 1 if x belongs to E complement. So what can you say about this f? What can you say about this F?
It is not measurable.
Yes, why is it not measurable?
Because inverse of 3, I mean 3
Exactly.
minus epsilon and 3 plus epsilon is not in.
Yes, others. Why is F not measurable? Yes, others. Please. I want others also to answer. Please answer. Why is it not measurable? Should I call the names? Manish? Manish Chauhan.
Yes, sir.
Why is it not measurable?
नहीं पता सर.
Govind Singh?
Sir, if it is measurable, then every subset of E, then F inverse of that subset should be in sigma algebra.
Right, very good.
But here F inverse of 1 is E complement.
Which is measurable?
Inverse 3 is B.
Is B measurable?
B is not in sigma algebra.
That's it.
That's why it's not.
Right, very good. F inverse of singleton 3 is not measurable. Right. Fine. So now we wanted a sequence. Fine. So we are going to make use of this function. Well, so do you know an example for a measure space which is not complete? Well, you look at R with the Borel sigma algebra and the Lebesgue measure, it is not complete. The proof is pending. So I'll do that once. So let omega equal to 0, 1. A equal to the Borel sigma algebra and mu to be the Lebesgue measure. Now you look at this function Fn from 0, 1 to R given by Fn of x equal to, we looked at this function minus 1 to the power n if x is rational and is 1 if x is irrational. Right. Now, see, we earlier what did we say? We said that Fn converges to 1 almost everywhere. Right. Now, you can also observe that Fn converges to this function f almost everywhere. But f is not measurable. So which means that the assumption on the completeness is very, very important. So in general, the function need not be measurable. Right. See, the only thing is that Fn, the almost everywhere limit need not be measurable. If you say that Fn converges to F almost everywhere, then it need not be measurable. But something else can be said. See, if you look at this example, we chose a specific F which is not measurable. But there was also yet another function G, wherein Fn converges to G almost everywhere, where G is measurable. So the question is, if you know that a sequence converges almost everywhere, does there exist a measurable function F such that Fn converges to F almost everywhere? The answer is in fact yes. So let Fn be a sequence of R bar valued Borel measurable functions. Well, of course, defined on omega. If the sequence Fn converges almost everywhere, then there exists a measurable function F such that Fn converges to F almost everywhere. If you look at this example, previous example, what is that was missing? There was a specific B, and on B the value changes. Right? So there is a non-measurable set wherein the value changes. So what do? Instead of this 3, change this 3 to 2 itself. Now this E is measurable and therefore F is going to be measurable. If you change this 3 to 2, which means on the whole of E, it is only 2. If you make this change, you haven't made any big change because measure of B is 0. In fact, measure of whole of E is itself 0. And once you make this change as from 3 to 2, you can notice that Fn converges to F almost everywhere and F is measurable. If you change this 2 on B to some other number, that is where the point is. So that's exactly what we are going to do now. Right, proof. So as usual, let E equal to all those x in omega such that Fn x converges. So since all these Fn's are measurable, by assumption E is measurable, also as Fn converges almost everywhere. Where mu of E complement is going to be 0. Right. Right. Now, so you want a limit. So how to get the limit? How to get the limit? What is the way to get the limit?
At E, we can define where Fn converges. So, and at E complement, we can take it to be some constant value.
That's it, done, right? Right. So now, so define F1 from E to R bar as F1 of x equal to limit n tending to infinity Fn x, right? So then F1 is A measurable. Now define F2 from E complement to R bar as any constant should help us. So let me simply write it as 0, doesn't matter. Right. So I've chosen, so it is, so then F2 is again, why is this F2 measurable?
Because inverse image is E complement, and that belongs to our
Inverse image of any set is going to be E complement, whole of E complement, and therefore this is a E complement measurable. So now define F from omega to R bar as F1x if x belongs to E, F2x if x belongs to E complement. Now
pasting lemma.
By pasting lemma, F is measurable and Fn converges to F almost everywhere. So if you change the function a little bit, then you should be able to get you can make the function to be measurable. That's the whole idea. Right. Yes, so the next one is what is known as, I don't have enough time. It's only, well, let me try to, well, the proof is not that difficult, but still. It is Egorov's theorem. Yeah. Fine. So let omega A mu be a finite measure space. And let Fn be a sequence of R bar valued Borel measurable functions such that Fn converges to F almost everywhere, where this F is measurable, because we haven't assumed anything about the completeness. So then, for every epsilon positive, there exists E in A such that mu of E complement is very small, it is less than epsilon, and on E, Fn converges to F uniformly. On E, right. Right. Yeah, maybe. Yeah, I have only given the statement. So maybe proof I'll skip to the next class. I don't want to get into the proof now. Yeah, okay. If you have got any doubts, please. I'll stop here because I don't want to get into the proof now.